Welcome to EDU World Space.
Once again, welcome to a new problem. This time we're given two blocks. One is called A, block A, and then we also have block B, and there's a spring in between them, and the spring is weightless, so has no impact pretty much other than the force it's exerting. The two blocks are sitting on a frictionless table. Okay, the two blocks are sitting on a frictionless table. That's what we're given. We're also given the fact that the mass of A, block A, happens to be 1 kilogram, and also the mass of block B happens to be 3 kilograms. That's what we're given. So initially, the two blocks are compressed close to each other, and then uh, they are released. The spring falls to the ground. So that's what we're given. And then travels in opposite directions. So A travels in the negative direction, and then B travels in the positive direction. The initial velocity of the system happens to be so initial velocity of A is 0 meters per second. Initial velocity of B is also 0 meters per second because they're not moving. The final velocity of A, that's something we want to find out. Okay, so we want to find out the final velocity of A. We don't know what it is, but we know it's moving towards the left. We're given the final velocity of B as being um, 1.2 meters per second. So that's what's acquired. So in part A, this is what we'll be looking for. In part B, we're going to see the relationship between we want to find out the potential energy. Okay, so find the potential energy in the system. So again, we don't have any friction. So there are no losses of energy using the law of conservation of momentum. We get to see that the momentum of the system, so the final momentum equals to the initial momentum because we have conservation of momentum. The final momentum is just the total momentum of, so MA, VA final plus MB, VB final. And that's the same as the initial momentum of the system, which is MA VA initial plus MB VB initial. Remember, we do have initial velocities of 0, so this was just going to be 0. Our goal is to get the final velocity of A, and so VA final, this one moves to the right. It becomes a minus MB VB final all over MA. We plug in the numbers, we get negative. Mass of B, as you can see, is 3 kilograms. We have to clear that a bit right here. So mass of B is 3 kilograms, so 3.00 kilograms, times the velocity of B, final velocity of B, which is 1.20 meters per second, divided by the mass of A, which happens to be 1.0 kilograms. 1.0 kilograms. And so our final solution for the final velocity of A becomes negative 3.6 meters per second. And that just means that it moves towards the left. Okay, this one means that the block, as you can see, is moving leftwards with the velocity of negative 3.6 meters per second. The second part of the problem, which is part B, was supposed to determine the potential energy of the spring. Remember, when the spring is compressed, it stores potential energy. So this is potential energy stored, and then when it bounces off, all the potential energy is transformed to the final kinetic energy of A, and also the final kinetic energy of B. Okay, so that's what's happening here. And so the total kinetic potential energy of the system is simply the final kinetic energy of A plus the final kinetic energy of B. And that's the same as 1/2 MA VA final squared plus 1/2 MB VB final squared. We change that to pull out the 1/2. We're left with MA VA final squared plus MB VB final squared. We plug in the numbers. The mass of A happens to be 1 kilogram, so 1.00 kilograms, and then we multiply that by the velocity of A, which we did find out to be negative 3.6 meters per second. We do have to square that, and then we add it to the mass of B, which happens to be 3.00 kilograms, and then multiply that by the velocity of B. The velocity of the final velocity of B is given as 1.20. So we have to use that 1.20 meters per second squared. That's what you have. And it helps us get the total kinetic energy of the system, which is actually elastic potential, not kinetic energy, but elastic potential energy of the system. That's what we're looking for. This one, we're going to call it elastic potential energy of the system. And that happens to be, if you divide those numbers very well, you get 8.64 joules. Hope you enjoyed the problem. Feel free to send any questions and comments, and we're looking forward to the next problem, and have a wonderful day. Okay, thanks. Bye.